Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. In this lecture series, we are going to discuss about FIR filters, FIR filter design using windowing method. Shall we start? Okay, see here. First of all, why do we need ideal filters? Why do we need filters? What is the use of filters here? Actually, FIR filter is Finite Impulse Response filter. Here we are going to discuss about what is the necessity of filters in biomedical signal processing. Here, one of the reasons why we design a filter is to remove disturbances. We know that very well. See here in this first diagram, signal S of n, which is mixed with the noise V of n, and it provides the output X of n. Here, the filter which takes the input X of n and it provides the output Y of n, which is a filtered output. We discriminate between signal and noise in terms of the frequency spectrum. See here in this first one, here our frequency is F and here our signal is S of F, and the frequency plot F0, and which has two parts, one is positive and another one is negative, minus F0 to plus F0, minus to plus, and finally we will get the signal with amplitude and frequency. The primary thing is we have to design a filters to remove disturbances, that's it. And in this we have two types, one is IIR, another one is FIR. In this lecture series we are going to discuss about FIR filter design. See here what are the conditions we have for a non-distortion. Here the problem is ideally we do not want the filter to distort the signal, we want to recover it. Here we have to maintain the same shape as S of t, just scaled and delayed. See here our input signal is X of t, which should be equal to S of t, that is our ideal signal. That is our output signal. We have to maintain the same shape as S of t, so that we need to scale and delay our output. See here our signal, first one is our signal, input signal X of t, which is equal to our signal S of t, and while it passes through ideal filter which provides the same output Y of t, but in practical conditions it is not possible, so we have to add some scaling and delaying function to our signal, then only we will get a proper output. Here our output Y of t, which is equal to AS of t minus t. Okay, here what are the consequences on frequency response? Here we have constant and linear. See here our H of f, which becomes a e power minus j 2 pi ft if f is in the pass band, 0 otherwise. See the signal. In this signal condition we have constant and pass band linear signal. If our signal in the frequency of pass band, which provides the output a e power minus j 2 pi ft in terms of frequency and time, 0 otherwise. See, for real-time implementation, we also want the filter to be casual. See here h of n equal to 0 for n less than 0, but y of n, which is equal to summation k equal to 0 to infinity h of k x of n minus k for past values only. Here the fact is, if h of n is casual with the finite energy, then the equation becomes integral minus pi to pi ln h of omega d omega less than plus infinity. Here the h of omega, it cannot be 0 on the interval, therefore it cannot be ideal. Because in practical conditions we do not expect the ideal output. See here the log of h of omega, log of modulus h of omega, which is equal to log of 0 is minus infinity, which in turn specified as integral omega 1 to omega 2 log modulus log of modulus h of omega d omega, which is equal to plus infinity. See the characteristics of non-ideal digital filters. See here, the first one is our ideal digital filter. Here we have taken only the positive frequency and See, in non-ideal filter, we have frequency response like this. First one is, see here, first one del 1, it is your pass band ripple, del 2 is stop band ripple, and omega p pass band edge ripple, and omega s stop band edge ripple. See the frequency transition, pass band, stop band, and in the mid we have transition band. In terms of del and omega, will represent pass band and stop band ripple, as well as pass band ripple and stop band ripple. See, first one is ideal filter. Here the output is perfect and it doesn't have any distortion. But while coming into non-ideal, in practical conditions, we have ripples in pass band edge and the star. Next one is classes of digital filters. This thing we'll see in next class.